Okay, thank you very much for the invitation. So today I'm going to talk about birational geometry of complex hyperbolic manifold. And so these are going to be like few joint works with Luca di Cerbo. Okay, so this joint. And so the main object of study of this talk are going to be exactly complex hyperbolic manifolds. So let me recall the definition. So we say that so a complex hyperbolic manifold, let's say a hyperbolic manifold, so it's a manifold with constant sectional curvature minus -1. So a hyperbolic manifold. Okay, so there exists only one hyperbolic manifold which is simply connected, which is the hyperbolic space. So in particular, any complex hyperbolic manifold is obtained as a quotient of the hyperbolic space. Okay, so we denote by Hn the complex. Yeah, sorry, holomorphic. Yeah. Thank you. Okay, so we know by Hn the complex hyperbolic space. So I was saying before, so if I have a complex hyperbolic manifold, then it's obtained as a quotient of the hyperbolic space more out a lattice in the isometries of Hn. So any complex manifold X, let's call it X naught, is realized as where this gamma is a lattice in the isometries of this Hn, which is isomorphic to P, U, and 1. Okay, so we don't need that. Okay, so I would like to understand a little bit better the birational geometry of this. It's a discrete, it's finite generated. So I mean, like, yeah. So I need finite generated, the finite generatedness because I want this to have finite volume. So I will explain it later. But so I want to understand the birational geometry of this object. So in case this manifold is a compact manifold, then it's somehow well understood. So if X naught is compact, then so this is a smooth variety with ample canonical class. Then and this follows from since this is quotient of the hyperbolic space, then this manifold has a Keller-Einstein with negative curvature, which is in the class of the canonical, minus canonical class, and then you get the ampleness from the Keller-Einstein. So what I'm going to focus in this talk is when this quotient gives a non-compact manifold. Okay, so if X naught is non-compact, then there is a very nice compactification, which is usually called Baily-Borel compactification. And so basically, so let me draw a picture. So I have a non-compact manifold, and I'm assuming also with finite volume. And this follows again because this guy is a lattice. And so the picture that one should have in mind is something like this. So you have something with a compact core, and then you have finally many ends, like infinite ends. Well, so I have finally many of these guys which are called cusps. And they all carry finite volume, even though they are infinite. And so this Baily-Borel compactification basically shrinks down to a point the finally many cusps. Okay? So I have something of this form. Okay? And so this is the Baily-Borel compactification. So it's possible. So this Baily-Borel compactification basically only adds finally many points to compactify this variety x0. So there exists a compactification x star such that, so when I look at the complement of x0 in x star, it is just finally it's composed by finally many points, such that x0, so x star minus x0 is a union of finally many points. Singular points, okay? Okay, so this work was done by Baily-Borel in the arithmetic case, and in general by Siu and Yao. Okay, so this object is getting more familiar in algebraic geometry, but so what I want to do is, actually we can resolve the singularity of x star, and we are going to get a smooth variety with a configuration of divisors coming from these singular points. Okay, so yeah, I need a mild assumption on the lattice that I will explain later. So under so we can resolve x star. So we get a pair x d. So x is the resolution singularity of x star. So where x is smooth. And this divisor d, which is the exceptional divisor, is a sum of irreducible divisor di, which are all disjoint, and there are abelian varieties. So smooth, where d is smooth, di are abelian varieties. And they are disjoint. Okay? So the assumption on the lattice is a little bit technical, but so it's a very mild assumption. For example, there always exists a finite index subgroup on the lattice such that that thing holds. So it means that up to a finite cover of the non-compact variety, you always get that assumption. Maybe if I have time, I'll explain it better.
But if you want to reach the assumption how wide it's free.
Yeah, so this is free because I want this to be smooth. But so it's something a little bit more. So basically it's something in the action of some elements on some neighborhood of the cusps. Okay, but so it's not.
And your hypothesis is just okay.
Yeah, And so I will refer as this pair as a toroidal compactification of X naught. XD is a toroidal compactification. And so from now on, I will work with these toroidal compactifications. And I would like to understand how the birational geometry of this pair gives information on the geometry of X naught. And so the first thing to notice is the log canonical divisor, Kx plus D, has some positivity coming from again from the Keller-Einstein on X naught. And so one can prove, so it needs a little bit of work, but one can prove that this thing is big and F. So this means that Kx plus D dot C is greater or equal than 0 for any C curve in X. And bigness is if I look at the pluricanonical maps of some large power of this divisor, then I have something which is birational. But in the nef case, then it's just saying that Kx plus D to the n is positive. Okay, but
isn't it already same?
No. So I'll give you an example.
But I mean, what's the polarization on the Baily-Borel?
Yeah, but when you pull it back, you get exactly this guy.
Oh,
Okay, so that's another way of saying why this is big enough. Okay. So notice that this divisor is never ample because when you restrict it to the boundary divisor, then you get something which is trivial. So but it's never ample. Okay, so for most of the application that I would like to explain, then I really need to understand the positivity of the canonical divisor itself and not of the log canonical divisor. So for example, there is a classical problem is to bound the number of cusps in terms of the volume. So the volume is the Riemannian volume of the variety. And so in order to do that, I really need to understand how positive is the canonical class. Okay, so there are few results
Volume is the same as the Kx plus D to the n.
up to some constant that depends on the dimension. And so there are few results going this direction. So probably the most important is a result of Mumford. So that says that in this setting, so up to a finite cover of X naught, then when I compactify, I get something of general type. So Kx is big. Okay, so this Mumford maybe tie in the non-arithmetic case. So up. Of X naught, then. So let's say Kx is big. So this again means that I take an étal cover of X naught and then I compactify the new variety that I get. And over there, the toroidal compactification has big canonical class. And this is just codimension of Kx is maximal. Okay, so one expects some kind of positivity on the canonical class, but the problem of this theorem is that you don't have any control on the étal cover. Okay, so it's not going to be very useful in the application that I have in mind, but so it's a first step.
Now X is one of the toroidal compactification.
Yeah, exactly. But X,
Then the X will be
Say that again?
Kx will be m.
No. I'll give you an example. So at x. Of the toroidal color. Okay. So one expects some kind of positivity, especially because you have this Keller Einstein that you really would like to say something on the canonical class. But so the important thing is Hirzebruch construction of few examples where so it showed that in general you cannot expect anything on the canonical class, so in this example the canonical class is not going to be nef. So in particular it's not ample, it's not globally generated, so you don't have much. Okay, so let me try to explain the examples. Okay, so we start with an elliptic curve. So let's take E into B, C, now this lattice. Where tau is E to the I pi divided by 3. So here you have a complex multiplication. So this is going to be important for later. And so we set Y to be just the product of E times C. And so in Y we have like four elliptic curves that are going to be important. So let X and Y, XY be coordinate on, so the coordinate X and Y here on Y. So we have 4 elliptic curves. Basically defined by X equals 0, Y equals 0, then you have the diagonal X equals Y, and then you take X to be tau Y. Okay, so we have, in Y we have configuration of these 4 elliptic curves. Something of this sort, okay? So E1, E2. Okay, so then Hirzebruch. So this Hirzebruch construction is you just blow up the point here, and what you're going to get is exactly the toroidal compactification that I wanted. Okay, so let X be the blow up at the origin of Y. And so the thing that the why I choose this tau is basically because it's an easy computation that E1, E2, E3, and E4 they intersect only at the origin. Okay? And so when I blow up and I look at the strict transform, I get 4 curves which are disjoint. So let DI be the strict transform of DI. Okay, so by the choice of tau, these DIs are disjoint.
And
Yeah.
so actually the tau
No, I don't think so. So I can do the computation later. So it's a little bit, yeah. But yeah, no, pretty sure. Okay, so if you blow up this thing, then there are going to be these joints, so I get something on this. So these di's, and then the exceptional divisor. And so I claim that xd is a toroidal compactification. It's a toroidal meaning it's a toroidal compactification of a hyperbolic surface. And so how do we check this so basically there is a theorem of Tian and Yao that says that if I have some equality between Chen classes, then I get this a toroidal compactification, and the theorem says that I have to check so we need to check so if I take C1 square of, so basically I want this shift with logarithmic poles along D, then this has to be 3C2 of the same thing. Logarithmic poles again. And so if you do a little computation, this is exactly kx plus d squared. And this is exactly 3 times the topological Euler characteristic of the open set. So kx minus kd. And so this is 1, because these are elliptic curves, and this is a blow up on elliptic surface of an abelian surface. And then this guy is -1 plus 4. And you get 3 equals 3. And then by this theorem of Tian Yao, we get that x minus d is covered by the hyperbolic space. So by Tian Yao, x minus d is hyperbolic. Okay. So in particular, in this example, kx has codial dimension 0 and is non-nef because it's the blow up of something with trivial canonical class. It's the blow up. Actually, one can generalize a little bit this example, and if you so say that you act with the subgroup of n torsions in here, then you can act on these curves, and so you get actually a lot more of this configuration in the same variety Y.
But I mean, this is a dimension for canonical.
Yeah, that's what I will try to explain. Okay, so if you let if you define un to be a set of xy such that nx and y is trivial, it's 0, 0. So the n torsion points, then if you act with this group on our curves, EI, then I get a lot more. So these are and so I get this configuration of like 4 n squared curves, or yeah, something like that. And they're going to intersect at n to the 4th points. Okay, so intersection point. N to the 4th. And so basically you have to blow up n to the 4th points on Y, and you do the same computation, you get again that is a toroidal compactification. And in particular, over here, the canonical class is as negative as you want top self-intersection. Okay? Those are So these are Hirzebruch examples, and basically they are the only examples that I know of these toroidal compactifications. And so what I want to explain is that this is actually, so it's not possible to generalize these examples to higher dimension. And actually something a little bit more. So let me write over there. So the theorem that we proved is the following. So let, again, xd be a toroidal compactification. So if dimension is greater or equal than 3, then kx is nef. So you're supposing non-negative intersection with any curve. Okay? And so this is exactly a surface phenomenon. Okay? So I would like to try to, so actually we proved something more. We proved that kx plus alpha d is ample for any alpha in 0, 1. Okay? So I would like to explain a little bit of the proof of this result and then give some few applications. No. No, so we don't have any example. So we can prove that after, but they are not going to be hyperbolic. So there are examples of toroidal of other things, not of hyperbolic manifolds.
But I mean, the numerical dimension is always at least n minus.
Yeah. So that's easy. So that you can prove that.
You mean that for n greater than 3, the examples of non-arithmetic lattices?
I'm not assuming.
One day of it. I don't know about higher. I don't think so.
I'm not assuming that lattice to be
No,
arithmetic.
no, but I'm saying this would be an indication of something changing from surfaces to 3 in connection with arithmetic. Oh, that's not.
Okay.
That's not known, but I was just looking for something that changed.
Okay. And so actually, let me give like a very quick application. So there, which was this. I told you that there was this classical theorem that you can bound the number of cusps of a hyperbolic manifold in terms of the volume. And so the number of cusps is exactly the number of components of the divisor D. Number of cusps is exactly the number of components of D, which, so now by this theorem, so if I take 2 times kx plus d, that is an ample divisor. And so this the number of components is less than or equal than d times this guy, because it's an ample divisor. Then you can compute this, and this is -1. Okay, so it's enough to bound this top surface intersection. And this is easy to bound. Again, you use again this theorem. Because we know that this one is strictly positive. And so if you do the computation, you'll get that this number is less than kx plus d to the n. Okay, which, as Janusz was saying before, this is some constant that depends on n. So it's for something like this. The volume computed with the induced matrix of X. And so you get, and so this is actually we get better bounds than Parker's result, than the classic result in topology, in differential geometry. Okay, and then this application is really easy from. There are other. What's the question? So the first bound was given by Parker, but with completely different techniques, and this bound is much better. Then there are a few bounds that are better in. Yeah, so I don't remember. So, but they have constant here, which depends on n. Okay. So
It's just the constant.
no. So at least Parker got something which is a polynomial in the kx plus d, which is not a linear polynomial. So it's kx to something else. No. For Parker's result, no. To some power, yeah.
And I mean, is it known that asymptotically grows like volume?
No, I think asymptotically one can get slightly better bounds.
I'm asking.
No, we don't know. I don't think so. No. So you want something like the reverse inequality? No.
I think you can, because if you take the finite index of the cusps, you can have.
Yeah, but so if you take finite index, yeah. And if you take finite index, you're going to some metal covers, which is not clear how the number of cusps change. So if I have time, I'll explain a few other applications of this theorem. And so I want to explain how the proof goes. And so our approach is completely different from the old ones, and we use it's just some minimal model applied to this setting. Okay, so it's going to be easy minimal model. It's not too technical. And so I want to understand so the nefness of this canonical class. And so if you assume that it is not nef, then there is the famous Con theorem that explains how the canonical class can fail to be nef. So let me explain Con theorem. So I will denote by an E bar of X. So this is the con of effective curves. So it's the closure of effective one cycles. And this is in N1 of X. So this is effective, there is a one cycles modulo numerical equivalence. Okay? So I'm looking at this effective one cycle modulo numerical equivalence. And so the Con theorem says that, Con theorem says that if I look at NEX, this can be decomposed as effective cycles with positive non-negative intersection with the canonical class plus a countable sum of extreme arrays, and these extreme arrays are generated by classes of rational curves. So where Ci is a rational curve. And also we know a bound on the intersection with the canonical class. So with Z is always less or equal than the dimension of X plus 1. Okay, so we know how to decompose at least the con of effective one cycles in the negative part negative with respect to the canonical class. So the intersection of CI and the canonical class is going to be very important for us. And so let me define a little terminology. So let R be a kx negative extreme array. So this is an extreme array of this cone, and so the classes in this R are supposed to have negative intersection with kx. Okay? So then the length of R is defined as, so I take the minimum of those intersections. So that the minimum minus kx dot ci, and this is for any ci in, so the class of ci is in the extreme array, and I want ci to be, sorry, for any c in the extreme array and c rational curve. Okay. And of course, so the same of the minimum of the cone theorem says that this length is always less than or equal than dimension of x plus 1. And the other thing that I need is the contraction theorem, which is usually considered part of the cone theorem, that says that I can actually contract extreme arrays, negative extreme array. That's a contraction theorem. So there exists a morphism phi r from x to y, which has connected fibers. So with connected fibers. And moreover, if I have a curve contracted by this morphism, then the class of the curve is in the extreme array. So connected fibers and C curve gets contracted. If and only if the class of C is in the extreme array. Okay? So these are very classical theorems in the minimum model program. So I would like to apply these theorems in our setting. Okay, let's see. So the main advantage in this setting is that we know that we have few rational curves. So we cannot have a rational curve in the complement of D. Because otherwise I would have a Keller-Einstein with negative curvature on a P1, which is not possible. So but notice that X may have rational curves, like Hirzebruch examples. So you are blowing up. Okay, so the first thing to notice is that this thing that I said implies a strong condition on the fibers of VR. So the fact is the dimension of fibers of VR is less than or equal than 1. And so how do we prove this? So let me do it quickly. So say F be a fiber, and C a curve in F. So C gets contracted, so it has negative intersection with the canonical class. And so since Kx plus D is nef, then we know that D dot C has to be positive. Okay? But so the other thing is that, so one has to study, so basically, so if you, one has to study the normal bundle of D, and this implies that this curve C cannot be contained in D. Okay, maybe I'll skip this, so but this implies that C is not contained in D. And so if I intersect F with the divisor D, I have something of 0 dimension, because it cannot contain any curves. And then this implies that F has to have dimension 1. All right? So this was easy. And so there are like a lot of theorems. Yep. But it's not a rational curve. So there is a theorem of Wisniewski that says that you can actually control the length of the stream array using the dimension of the fibers. So Wisniewski. So I'm going to use two theorems of Wisniewski. So the first one is length of a stream array is exactly less than or equal than the dimension of F, and F fiber of phi plus 1. Yeah. X is smooth. Yeah. So X smooth. Thank you. Okay, so the first one is this one. And in particular, I get basically very easily that the length of extreme array of a hyperbolic manifold is always less than or equal than 2. And then the second theorem that I need is that if we are in this case exactly when length is less than or equal than 2, or like dimension of F is less than or equal than 1, then we can actually classify all extremal contraction that we get from this theorem. So if dimension of F is less than or equal than 1, then Y is always smooth, so it's smooth. And phi F is one of the following. So I either have that phi R. So we can have two cases. One is that is a conic bundle, and the other one is that is a blow up of a subvariety of codimension 2 in Y. It's a conic bundle. This means that each fibers is isomorphic to a conic in P2. Blow up of codimension 2. Actually, we can prove that Z is smooth. Okay. So this is what Wisniewski proved. And so we have to prove that these cases they cannot occur in the hyperbolic case. So let me say why it doesn't happen. So I'll write a picture. I'll draw a picture. So say that we are in case 1. So phi, so yeah, I'll write the X. Then this maps to Y. And so this is a conic bundle, so all these fibers are P1s, and then I have the divisor D. So D1, D2, D3. Okay, so I have a lot of rational curves. And so the key observation is that a rational curve had to intersect the boundary in at least 3 points. Because again, otherwise I would have a metric with negative curvature on a P1 minus a point, or P1 minus 2 points. So the key fact that D dot of fiber F is always greater than or equal than 3. Okay, so for any of those fibers, then they have to go through at least 3 of these boundary components. And so now I contract this back to the Baily-Borel compactification. And so I have all these singular points coming from the components of D, and then all the fibers have to go through all of these points. So at least 3 of these points. All right, so we have something like this. Okay, so in particular, I have a family on this Baily-Borel compactification of rational curves with a lot of fixed points. And so then we can apply bend and break. Bend and break says that if I have a family of such rational curves, then they are going to break at some point. Okay, so in particular, this means that I have a reducible fiber over here. Okay, because the curves that breaks corresponds to a reducible fiber. But now since dimension of y is greater than or equal than 2, so greater than or equal than 2, yeah. Then I have at least a one-dimensional family of these irreducible fibers. So I can reapply bend and break in the same way, and I get a fiber which has 3 components, which is impossible because it's not a conic in P2. Okay, and so the other one is exactly the same thing. It's a little bit easier. So basically, for the other case, then we still have this X. Now I have this P1 bundle, which corresponds to the exceptional divisor when I blow up Z in Y. Okay, and so again, since I'm assuming the dimension of Y is greater than or equal than 3, then I actually have a family of rational curves. And again, I have the boundary components has to go through this, then I contract again and apply bend and break. So I have a reducible fiber here, which is not possible. So, but this example really explains why this fails for surfaces. Because if Y is a surface, then I get only one rational curve blowing up. And so I don't have the family, and I can apply bend and break. So this is not possible. So, and of course, you will expect that because of Hirzebruch examples. But in this case, you can work a little bit more, and you can prove it even for surfaces. Okay, so there are no like toroidal compactification which have a conic bundle structure. Okay, so this somehow explains why Kx is always nef. And to prove this other one, that Kx plus alpha d is ample, then you do something similar, but instead you use the Kohn theorem for KLT pair. And basically you prove that this thing is strictly nef, then you apply base point freeness, and you get the ampleness. But let's not do that. So actually this implies something also for, this proof implies something also for surfaces. So if X has dimension 2, then we can prove that kx plus alpha d is ample for alpha in this range, so 1/3, 1. So in Hirzebruch examples, you get 1 divided by 4. So this is not sharp, basically. But so using similar ideas, you can, for example, we get a sharp cusp count for surfaces. So we get the number of cusps is exactly less or equal than 4/3 kx plus d square. And again, equality is achieved exactly for Hirzebruch examples. So I would expect that Hirzebruch examples give the sharp bound also for this theorem, but I don't know how to prove it. And exactly it comes from this inequality. So in Hirzebruch examples, you always get that d times a rational curve is greater than or equal than 4. And so if you want to be able to prove that, then you get 1/4 over there. But there are no examples where you have a rational curve that intersect the boundary only at 3 points. Okay? And so let me state at least one other application of this. And also another thing, so I was really interested in understanding if the codal dimension of these varieties is always positive. So by that theorem, if you believe in abundance, then it should be always positive. But I have no idea for surfaces. So the question that
Can you explain to what it gets and something?
yeah, so if you believe abundance, then
Well, then it can be 0 by kx.
yeah, I want non-negative, sorry.
Something else.
Yeah, no, I want non-negative.
But the numerical dimension is that manifold because it's kx restricted to the can you explain?
So I want non-negative codal dimension. I would like to prove that they always have non-negative codal dimension. Okay? And so but for surfaces, I have no idea. So we have no idea. Which seems an easy question, but actually, so it's very hard. So the numerical condition does not give anything, basically. Okay? So let me state a few applications. So I said that kx plus d is big enough. And actually, if you take a large power of kx plus d, then you're going to get back the Baily-Borel compactification. And you can find an effective power using this theorem. So the thing is that if, so m kx, so this linear series, so that the map associated to the linear series, so define gives a map. So we image the x star for m greater than or equal than some constant like this guy. Depends only on the dimension. And so this is important because so you can prove. Say that again. So, yeah, 3. Sorry, okay. And so this is important why you can reprove, maybe improve a little bit of a classical theorem of Wang that says that if you have a hyperbolic manifold with bounded volume, then there are only finitely many of those. And so using this, you can prove that. So there are only finitely many x.
Please tell me the question.
Yeah, is theorem, yes. Yeah. Bigger than 3, yeah. So there are only finitely many x arising as toroidal compactification of hyperbolic manifolds. Of volume less than some fixed volume, and of course of fixed dimension. Question? Okay. So
What are you saying? You get an actual bound while he just has his theorem probably doesn't.
So his theorem was only on a hyperbolic manifold. I'm saying also the compactification are finitely many, and you can actually get an effective bound. So you can write down the function. And of course now, so the key idea of this thing is that once you have this theorem, then these toroidal compactification, they come with in some sense with a canonical polarization. So you always have a fixed ample divisor.
So what's your bound?
It's some ugly. I have the formula if you want to see that. So basically you embed your variety in some Pn, and then you have to use a formula on the connected component of some Chow varieties, and so it gets a little bit complicated. But the key point is that you have this canonical polarization, and the top surface intersection of that ample divisor depends only on the volume of the hyperbolic manifold. And so you get all of these plus this effective. So you need the effective embedding theorem. Okay, so I think I'll stop there.